Hello math friends, this is Precalculus section 7.1 day 1 notes. We are going to start chapter 7 with a discussion of some trigonometric identities that we should already be familiar with. The idea that sine is the reciprocal of cosecant, cosine is the reciprocal of secant, tangent is the reciprocal of cotangent, and then vice versa. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. And then also that we can think of tangent as being sine over cosine, therefore cotangent is cosine over sine. Then we have our three Pythagorean identities. The sine squared x plus cosine squared x equals 1. That comes from our equation of the unit circle. And perhaps you didn't know, but the other two Pythagorean identities, 1 plus cotangent squared equals cosecant squared, and tangent squared plus 1 equals secant squared. Those two identities just come from taking the original Pythagorean identity and dividing it by either sine squared or by cosine squared. So the first one, and again, you don't have to write this down, I just want to show you this. If I divide by sine squared x all the way across this equation, sine squared over sine squared becomes 1. Cosine squared over sine squared becomes cotangent squared x, and 1 over sine squared x becomes cosecant squared x. So you can see how if I divide the original Pythagorean identity by sine squared, I get the second Pythagorean identity. And then if I were to divide the original Pythagorean identity by cosine squared, like so, sine squared over cosine squared is tangent squared, cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared x. So you can see that I've just derived the third Pythagorean identity by dividing by cosine squared of x. So just a little background on where those came from. And remember, there is that poster on the ceiling if you ever need it. Then we have our even-odd identities. We learned these in a previous chapter, chapter 5 actually, that sine of negative x is equal to negative sine x. That's because of the shape of sine. Cosine of negative x is equal to cosine x. Tangent of negative x is negative tangent x. And then their reciprocals have the same, behavior. Cosecant is also negative, secant is positive, and cotangent is negative. The new information here that we haven't seen yet are these cofunction identities. And basically what these are is just an explanation of how these functions can be transformed to become another function. So for example, the cofunction identity sine x equals cosine of pi over 2 minus x. That just means that we could rewrite a sine function as a cosine function if we shifted by pi over 2 units, right? That our sine function would look like a cosine function if we shifted pi over 2 units to the right or to the left. And same goes for all of these. That's where these cofunction identities come from. The idea that you could rewrite tangent as cotangent, rewrite cosecant as secant, cosine as sine, cotangent as tangent, or secant as cosecant. And again, all of these cofunction identities have pi over 2 in them, but remember, pi over 2 is equivalent to 90 degrees. So depending on the information that you're given in the problem, sometimes you might want to work in radians, and sometimes you might want to work in degrees. So our following two examples, we have one example of each of those things so you can kind of see what I mean. In our first example here, we want to use a cofunction identity to answer sine of pi over 6. Now hopefully you're thinking about the unit circle right now, and you already know that pi over 6 is our first radian measure on the unit circle. Sine is going to be the y value, so we know sine of pi over 6 is 1/2. Okay, so we already know the answer to this question before we've even begun. But our job is to use a cofunction identity to explain that. So since we are given sine of pi over 6, we're going to start with the cofunction identity that says that sine of x is equal to cosine of pi over 2 minus x. All right, so in this case, we are going to, our x value is our pi over 6. So we're just going to rewrite this. Sine of pi over 6 is equal to cosine of pi over 2 minus pi over 6. And then, of course, we want to be able to subtract the radian measures inside the parentheses. So I'm going to make a common denominator. So I'm going to make pi over 2 into 3 pi over 6 minus pi over 6. And then 3 pi over 6 minus 1 pi over 6 would be equal to 2 pi over 6, which is equal to pi over 3, right? And then we know that the cosine of pi over 3 is 1/2. So basically just showing us that sine is a transformation of cosine, or cosine is a transformation of sine. Now we can do the same thing with degree measures. So in the second example here, we have tangent of 47 degrees. So this time we're going to start with the identity that says tangent of x is equal to cotangent of, and since I'm working in degrees, I'm going to write 90 degrees minus x instead of pi over 2 minus x. So my x value is going to be my 47 degrees here. So tangent of 47 degrees is going to be equal to cotangent of 90 degrees minus 47 degrees. 90 degrees minus 47 degrees is, of course, 43 degrees. So we end up with cotangent of 43 degrees. Now this is not a nice value for us on the unit circle. So at this point, I would grab my calculator. Remember, first of all, that you need to be in degree mode because we are doing trig functions and we're working in degrees. Cotangent is the reciprocal of tangent, so you would type in 1 divided by tangent 43 degrees. That would give you your cotangent, and you should get 1.07 for your answer. The next thing that we're going to talk about are our techniques for simplifying trigonometric expressions. There's a big poster on my wall, kind of near my desk on the window. It's orange and yellow, and it has these techniques on it. These are things that you're going to be referencing frequently, that you're going to be going to as we work on either simplifying or verifying trig expressions in the next 2 sections. This is kind of going to be the big work that we're going to be doing for the problems in both of these sections, and it can be challenging. So the first thing that you can do is you can substitute an identity. And usually we're thinking about our Pythagorean identities, but remember we have our even odd identities and we have our reciprocal identities as well. The second thing, and probably the thing that you are going to use most often, is going to be to change all of your terms to sine or cosine. Another technique is to multiply by a form of 1. And this might be if you're trying to make a common denominator or something like that. So an example would be if you were to multiply everything by tangent x divided by tangent x. That's just like dividing by 1, but it might help you transform your expression. Our fourth technique is going to be to get a common denominator. You will often do this if you have 2 expressions on one side of an equal sign and you're trying to make it look like one expression on the other side of the equal sign. So you need to combine them together with a common denominator. Technique number 5 is to factor, and hopefully you know it when you see it. Either there's going to be a GCF or there's going to be a trinomial of some sort, and it's hopefully going to be very apparent that you're going to need to factor. And then finally, sometimes we have to multiply by a conjugate. Now remember, when we're multiplying by a conjugate, we are always changing the sign in the middle of the expression. So let's use some of these techniques and try a couple of the following simplify examples. In example number 1, we're going to use that second technique, which I said you're going to be using all the time, and that is to change everything to sine and cosine. So the first thing I'm going to do is I'm going to take everything in this expression and I'm going to rewrite it in terms of sine and cosine. So tangent x is going to be equal to sine x over cosine x. Cosecant x is going to be equal to 1 over sine x. This is all in my numerator. And then my denominator, which right now is secant x, I'm going to rewrite as 1 over cosine x. Then, of course, my next step is going to be to keep switch flip since I'm dividing fractions here. So my numerator is going to stay the same. Now my sine x's, and another way you could look at this too right away is you could say my sine x's are going to cancel, right? Because I've got 1 above and 1 below in my numerator. So my numerator is really just 1 over cosine x. My denominator is 1 over cosine x. So when I keep switch flip this, I end up with 1 over cosine x times cosine x over 1. Or of course you could have just said, I'm dividing 1 over cosine x by 1 over cosine x. I already know that my result is going to be 1. That's not so bad. In example number 2, we're going to try the same technique. We are going to rewrite everything in terms of sine x and cosine x. Our numerator is already cosine x, so that is going to stay exactly as it is. Our denominator, we have secant x minus tangent x. Secant is the reciprocal of cosine, so I'm going to rewrite that as 1 over cosine x, and tangent x is sine x over cosine x. So look at that. My two terms in my denominator, when I put them in terms of sine and cosine, already have a common denominator. So in my next step, I am going to rewrite the denominator. I've got 1 minus sine x all over cosine x. And my next step then is going to be to keep switch flip because I'm dividing my numerator by my denominator. So I've still got that cosine x. You could think of it as cosine x over 1. And now I'm going to be multiplying it by cosine x over 1 minus sine x. I did a keep switch flip here. So now my numerator, cosine x times cosine x, becomes cosine squared x. And my denominator is still 1 minus sine x. Okay, so now this one is quite a bit more complicated because at this point, there's not any more simplifying I can do, but yet I know that this can't be it, right? This is still kind of too complicated to leave our answer in. So now that I've got a cosine squared in my expression, the next thing I'm going to think about is, well, my Pythagorean identities always have squared terms in them. So if I look at my first Pythagorean identity, sine squared plus cosine squared equals 1, if I solve that for cosine squared, right? So if I move that sine squared over to the other side, cosine squared would be equivalent to 1 minus sine squared x. So that's the next thing that I'm going to do, is I am going to replace this numerator here with a Pythagorean identity. Okay. So my cosine squared x, I am going to rewrite as 1 minus sine squared x, and this is over 1 minus sine x. Now don't go and try to get cancel happy on me. We can't cross those out. Notice that our numerator is sine squared and our denominator is just 1 minus sine x. So we can't do any canceling yet. However, here's an important thing that you may not be thinking about because we're working with trig functions, but you need to be thinking about it all the time. This numerator is a difference of squares. So it can be factored. So if we factor our numerator, this is going to become 1 plus sine x times 1 minus sine x. And our denominator will remain 1 minus sine x. So now we can finally cross out that 1 minus sine x that we have in the numerator and the denominator. And our final answer here is going to be 1 plus sine x. And that is going to be as simple as it gets. So as you can see, our second one here was quite a bit more complicated than our first one. And sometimes that is the case. You just have to be patient and keep working through it.